Hello, my name is Leonildo. I am a PhD student at the University of São Paulo, and I will present the work A Performance Evaluation for SIG JSON Tokens in Access Control for the Cloud of Things. This work was carried out into the LazyPC and supported by CMA. This work was motivated by problems related to the low security in the Internet of Things, the empirical analysis of the encryption algorithms used, and also deficient literature in works involving the use of tokens for IoT. In this context, our objective is present our architecture built for evaluation for the selection of JSON tokens in Internet Access Control of Things. And basically, our main goal is to support the researchers and developers in the best token configuration for the application scenario. It's possible to find in the literature some works that use both tokens and algorithms. However, they don't explain how exactly the token is built or even the token data structure. And also, the performance evaluation in these works is quite simple. So this picture shows our visual model of the visual model of architecture. First, we have a resource owner or a resource information owner. Then we have a client component. Basically, it's any client application. Then we have another server. We call the server broker. Then we have other two servers. In this case, we have two possibilities, two scenarios here. In the first one, the broker only passes the information, the request, to the authentication server. In the second scenario, the broker makes also a load balance between two authentication servers. So in the first case, we have only these machines. In the second case, we also have another authentication server. So how is it work? First, the resource owner insert the user and password in client, in this case JMeter. Then the client requests a token to the broker. In the first case, broker only just passes the information forward. And then the authentication server verify if the information, the data is everything okay, then he returns a token, and then broker returns the token to the client. And now after the client get the token, he can get the data following the same path request, and in this case with the request comes together the token, and then the broker, the first case, only passes the request, or in the second case the broker makes a load balance between these two authentication server, and then return following the same path than before. Okay. Here we have the JSON data structure, the JSON token data structure. First, we have a username and the authentication with the rules, and we also have here the client ID, because we could have many client applications and then we need to identify which one of them requests this token. It's quite simple. This figure shows the response time composition, basically divided into 5 points. First one, the connection time in the client. Second one, the communication time between the client and broker. Then the processing time spent by the broker. And also the communication time between broker and API. And finally, the API time. Just come back here. So point 1, the client. Point 2, communication between client and broker, 0.3 the broker, and 0.4 connection time between broker and authentication server. And here the API is composed by authentication server and the database. Okay, so 1, 2, 3, 4, and 5, all of this time here. In this table, we show all of the collected metrics. So, however, I won't detail one by one, do it to the time. In this case, I mean the percentage time, not the metric times. But basically, we have another table here with more details, where, for example, times CB. What's times CB? We can come back here. Times CB is time spent on communication between the client and the broker. Okay, and how is calculated that? We can calculate by G, the variable G. G is equal the elapsed time, the total time, minus the connect time, minus request time. Quite simple. So we can come back here to see what means any of these metrics. And okay, the second table on this page shows the experiment parameters. In this case, we have a factor and levels. So we did a complete factor experiment where the factors are architecture, request total, requisition type, equal to graph. In the first case, the levels are proxy, and proxy here, I mean, it's this first scenario without a load balance, and the second level, it's the architecture with a load balance. So also the requests, 1,000 requests and 10,000 requests. Also the type requests, get access token or get data, and two algorithms, the ATMAC, asymmetrical and asymmetrical, the RCA algorithm, encryption algorithm. Oh, sorry. And I also have a fixed parameters, but I won't detail this part. This picture shows the visual model of the environment setup, or also the experiment setup, where we have 10 clients, so 10 JMeters. Also, we have the broker. In the first case, again, the broker only passes the information, the request forward, and you have only one authentication server in the first case. In the second case, we also have another authentication server, sorry. And in second case, the broker makes a load balance between both hosts, both servers. Okay, it's quite simple as well. And okay, we also have an agent in each host, each machine. This agent collected some additional metrics like CPU usage, memory usage, and disk usage, only to evaluate the hardware performance. Okay, this table shows the RSA response time with load balance and without load balance. Here, I put this table only to show how the metric is collected. Okay, one by one, but it's not very important at the moment. The important is this graph where we identified the bottleneck. We can see the API, the authentication server in this case, plus database, took almost 90% of the total time. The same here. Here was worst, almost 100%, 97%. Both experiments was 10,000 requests. The first one without load balance, and second one with a load balance. We can see also here that the response time decreases dramatically in this case. Look, without the balance, it took almost 1 second. In the second one, with a load balance, took only 50 milliseconds. Here, I had the same result in this part, half to right. And in the left, I have the results to 1,000 requests. So few requests and many requests. We can see that the RCA algorithm took a lot of time more than 8 meg. However, on the other hand, if I with a load balance, this time decreased dramatically. The same result here, and we also can see that the difference between one scenario and one algorithm and other algorithm is quite low. Okay. This box plot shows the experimental behavior. We can see with 10,000 requests and without the balance, the asymmetric algorithm, in this case RCA algorithm, looks a kind of chaotic. It's like a kind of chaotic. And with a load balance, the time has an improvement here. Okay. I want to see the behavior, the time behavior. This another graph shows the CPU and memory usage. The first one with RSA algorithm, the second one with 8 meg, both with 10,000 requests. We can see that CPU usage was almost 100% in both cases. And again, if I execute the same experiment but with a load balance, this time decreases as well in both algorithms. So what did you learn with this work? For environments where the number of requests is very high, for example 10,000 requests, there's a cost in using asymmetric cryptography, the RCA, to sign the token. And in this case, using the broker as a load balance is indicated to decrease the response time. But if I don't have a load balance, maybe asymmetric cryptography should be better. Also, there is no significant difference in response time when using asymmetric or asymmetric signature. But in environments where the number of requests is small, until 1,000 requests, maybe it's worth using a more robust algorithm than asymmetric, for example. In this case, I recommend use the broker as a proxy only as well. Okay. In future works, we intend to insert new token sign algorithms and evaluate new scenarios with variation in key sizes for symmetric signs. So more options in token side. Also, we intend to evaluate scenarios with changes to the broker schedule algorithm. So we use a round robin, maybe using another algorithm we have other results. And finally, we intend to separate the authorization server from the resources, because in this case, the authentication server and the database are in the same API. Okay, also I leave my acknowledgement here to the funding agencies, CMEA, PAPESP, and CAPS. Also, I leave my thanks for you. Thank you very much for your attention, and I'm open to answer any questions from now.